Hello, everybody. My name is Julian Oppermann, and it's my pleasure to welcome you to the tutorial days of FPT 2021. As you can see, we have a packed schedule today and tomorrow, and I hope you will enjoy the talks and learn something new. I will also want to say many thanks to our sponsors, Intel, Xilinx, Bitware, Imagination Technologies, and Velocity for supporting the conference and allowing us to offer free registrations to everybody who's interested in field programmable technology. Our first tutorial today is given by Pablo Orduña of LabsLand on a very timely topic for the unfortunate situation the world is currently in, improving hands-on lab sessions with remote FPGA. Pablo, please take it away.
Thank you very much, Julian. I'm going to share my screen to start with the presentation. And I guess you can now see it. So thank you very much again, Julian, and also to Intel as a sponsor of this particular session. What we are going to present in this talk is first I'm going to explain a little bit of what is a remote laboratory, then what is the LabsLand network, and then we're going to go straight to the hands-on session. And then we can have any Q&A, but however, please also ask any questions in the chat of the tool and so on, and I will try to check from time to time. So the first part is remote labs. So first of all, what we are going to be calling here remote laboratories is any kind of laboratory that can be accessed remotely, so that the student can be anywhere, like in the classroom or at home or wherever, but they don't have to have physical equipment physically in that university or in that place, and they can access equipment such as FPGAs in this case, which are remotely available and which are located in other places, like in this case different universities and so on. So just to put an example, like before going to the FPGA part, this is one of the Arduino robot laboratories that we have in LabsLand. So basically here there's a robot that you can control with a camera and so on. And what the student sees is this, like the web version. So I'm going to load the video. So basically, the student sends a program, a code that they have built, and they will see the robot moving in the real environment in the remote laboratory, which is located somewhere else. So the student doesn't have to have the equipment or anything like that. They can physically connect to this robot, which is located elsewhere. Like in this case, I know by the camera this one is in Spain. So basically, the student can interact with the CL monitor and press buttons and so on to see how it works. The next part is the LabsLand network. LabsLand is a global network of real laboratories available online, including remote laboratories. Like we do not provide simulations or similar, but we are providing access to real equipment or in different forms. So for example, the Arduino robot that I was presenting before, we have many copies in many different locations, including in South Africa, in Costa Rica, in the United States, where we have here one robot, another one here, and two more here, and four more here. And we have it in different locations in different countries. So students access to any of the available robots. Like the student from this university will access first those in this university, but if all the robots are busy, they will go to robots which are located somewhere else, like in South Africa, or Costa Rica, Spain, or wherever. So they basically, all these resources are shared resources between the different institutions in a way that they can leverage the peaks of each other. So if there is a peak, because right now there's many students using one, they will be using all the other equipment which is located somewhere else. We also have laboratories like Arduino Board, which is also different, and electronics. This is another laboratory for where you have a function generator, a multimeter, DC power, and so on. And that we also have with different universities, partner universities in TU Dortmund, University of Georgia in the US, Costa Rica, Spain, and so on. And now coming back to the FPGAs, so this is how it looks, the FPGA laboratories that we typically have, which are the ones that we are going to use in this workshop. This is, for example, at the University of Washington, we have like 1, 2, 3, 4, 5, and there are more here, like another one here, structures. Each of these structures has 1 camera and 4 FPGAs, and that's what you will be accessing during the workshop. So you will be controlling the FPGA, which is remotely somewhere else, and you will be sending the code and so on. You will be able to see with the camera how it works. We also have other laboratories here of Texas Instruments, Arduino, and so on, but those are different. This is the ones of the University of Washington, but we also have in the University of Michigan. Here you see also other types of FPGAs, the D2115. In Monash University, we also in Malaysia, we also have the FPGAs of the D2115, different copies in this. At the university, the Public University of Navarre, same thing. And Unifesp, the University Federal of Sao Paulo, same thing. Like we have different copies and so on. So students go to any of the available laboratories. Students love it because they see that, I mean, in this case, they see it physically, but typically they see it only remotely, that they are using those laboratories. But they see that it's actually 100% real and so on. And actually, in the ACE conference in 2021, the University of Washington published an article that got actually the award of the ECE Division Best Paper Award. And the paper was about how students perform better in terms of overall scores, understanding skills, and analysis skills when presented to the remote access of the laboratory hardware than with the hardware in hand. I'm going to briefly also cover, I'm going to check just in case there's any question or something, which I heard like some comment, but okay. So just in case, like I'm going to also explain a little bit of other laboratories, because like the workshop is going to be focused 100% on the FPGA, but just to give a bigger overview of what other things are available. So like we have also in the same way laboratories of biology and physics. For example, this is in University of Queensland in Australia, this is in University of St. Thomas in Houston. These laboratories are different because what we do is we pre-record what the student can do. Like for example, in the case of the physics of reactivity, what we do is we have like 6,000 pre-recorded experiences with 1,300 combinations of what the student can do. So they can choose like a strontium and americium and something and different distances, and they will see a particular video of how that looks when you are using it. So they see a real video. They have still the feeling of that it's real experience because it is real. It is a real laboratory. But it's not happening in real time, and therefore, like you can have it with all the classes at the same time. We don't have to have multiple copies in multiple locations, and so on. In the same way, we have laboratories of 3D printing. This is at University of Salento in Italy, with different views. You can select what exactly you want to see and like what kind of piece. Like for example, if I go to this one very quick, I can show that. In this laboratory right here, and you will have access to these laboratories later on. So in this case, like there is a video of interaction explaining about the laboratory. You can select which kind of piece do you want, how you want to put it, like inside or top or how. You can select the thickness of the material you want to use. You can choose the printing temperature. You can select if you want to put supports or no. And if you start observing, like, so I did something wrong here with the thickness, like what you will see is like exactly what happens with the laboratory whenever you are starting to record it, and you can see how it moves and with the different views, like with the close view, with the perspective and so on, and you can see exactly how it's printing, and you can make it go faster or slower, and you can always test it again if you want to test with different parameters and so on. So the experience is real in the sense that you are seeing what happens in a real laboratory, but it's pre-recorded in that case. We have also centrifugal pumps in the same way, like chemistry at the University of Georgia, in TU Clausthal in Germany. We have also like a flow loop engine for petroleum engineering, like texture analyzer. Like all these are the ultra concurrent labs, those that are pre-recorded. So these are texture analyzer that you can like operate this instrument and see how what is the data that it's providing and so on. And also like a Pelton turbine and things and this is a thermographic camera. So in this case, like you can also select like how the servers look through this camera, and you have like several dozens of situations and so on. So and those laboratories, what we do is we partner universities like in South Africa and Costa Rica and like everywhere else, and they with them we select what to record. They do the recording with the materials they already have, because they are the ones who have the expertise, like in chemistry, for example, or in other fields. And what we do is we create all the laboratory around it, so that it's a useful tool that can be used in the classroom. It can be integrated in Canvas, Moodle, and other learning management systems, and so on. So to sum up, like we have the two types of laboratories: the real-time laboratories, like such as FPGA and Arduino, electronics, and so on. And we have the ultra-concurrent laboratories, which are those that we pre-record all the combinations and provide an interactive user experience for the student, so that they can see how it looks in the real world. And then like LabsLand is a network, so we have like many providers, like universities who provide their laboratories, and we also have like hundreds of consumers, like universities and schools, who use that laboratory through a subscription model. So right now we have like universities in 14 different countries, like in all the continents, but enough about the talks. I prefer like to go to the hands-on part of the session, so we can all play with the equipment and so on. So I'm going to show this link. I'm going to share it also in the chat. But like basically, like let me copy this link right here. I'm gonna put it in the chat in Zoom, but also in the other one. Presenter chat. This is a forum. I just share that slide. This link. If you follow that link, it will go to a Google document where you have other links, including like how to register in the platform and so on. So I know that some of you already in the platform. Let me see if I can see this. Like here, like a document with some parts, and the first link that you will see is the registration. If you go to this link, you many of you already have an account, because you received an email recently for this part, but some of you will already have created an account. Those of you who have not, it's totally fine. You can go to, hold on, this is not registration. I think I'm sending the link to the same place. Hold on. I'm going to change the link just in case it was not copied correctly. So that is the link to register in the platform. Like, let me also share it just in case in Zoom and so on, and in this tool. So basically, if you follow that link, what you will see is, well, not in my case, but if for everyone else, if I go into both, what you will see is this. So here you will have the option to either log in if you already created an account, or create a student account. Like, I'm sorry that it's like, I know you're not a student, but in this context, it's like the user one. So if you click here, you can create an account. Like, for example, if I'm going to create one called Pablo.Orduna, and you can put any passwords, and then it is optional. If you want, you can put an email, but that's completely optional. We will not store the email. This is only in case of if you forget the password or something like that. In my case, I'm not going to provide the password. And I already created an account at some point in this space again, so I'm going to try to I'm going to say FPT. And then once I create it, you will see a single group called FPT21 tutorial for FPGA, and I will be able to go to the particular laboratories. Additionally, like if I go back to the document, you will see that there are other links such as more labs, that if I copy this link and I open it here, I will see that I'm already logged in, so I can add myself to that other group. In that case, I will have two groups, the other labs, but if I go here, I will see both FPGA and other labs. So I will be able to see all other laboratories that I was presenting before, and I can click on them and access them and so on. But in this workshop, we're going to focus on the FPGA ones. So I'm going to go to one of them just to make a first demonstration on how this works. So for example, if I go to the D1 system chip, I will see that I can upload code in Verilog, in Vhdl, and in System Verilog. If I select, for example, Vhdl, I will go to one tool where I will be able to write my own code in Vhdl. Well, it will tell me like some instructions and so on. I'm going to skip them. But in this case, for example, this is a very simple example. I'm going to use another one. I'm going to delete this file, and I'm going to copy the code from here, LEDs mirror here, LEDs mirror. So right here, I will be able to, I have the code that I can again delete, I can add new files, I can add files from my computer and so on. And then once I have my code, that in this case is just a simple example, I'm going to be able to synthesize this code. For this, I'm going to be using Quartus. So I will see here all the compilation process and so on. As you know, that typically takes some time. Like in this case, it takes, for example, in some computer, it took 2 minutes and a half. However, given that this code has already been compiled in the past, we have a cache for it, so we don't have to compile it again. So in this case, that's why it took only like a couple of seconds to be programmed. So now this code, what it does, if I check, it has some LEDs and some switches. I see that there are 10 and 10. There are some buttons, like 4 buttons from 3 to 0. And then whatever button you choose, depending on the values, it will show some things or different things to the 7th segment display. So if I go to the upload to FPGA, what I will see is that given that I mapped the switches to the LEDs, with this code, what I will do is I will go to some equipment, in this case, one of the ones at the University of Washington, and then I see that for 3 minutes, I have access to the equipment, and whenever I click on the switches, I see that the LEDs turn on and off. So they are turning on. If I turn it off, it will turn off, and so on. So all this is actually right now happening at the University of Washington. So like I don't know where you are, but like I'm in Germany and I'm connected to this equipment, which is right here, and also with the buttons. Whenever I press them and I keep pressing, I will see 1, I will see 0, I will see 2, and I will see 3. So I will be able to see the different like a logic that whatever logic we were using in this design. As you saw, like for simple lessons like that, like the 3 minutes is usually more than enough. It depends on the complexity of the lesson, of course. But at any time, I can leave and if I leave, I will go back to the code editor. I can change the code. I can synthesize again the code, and then I can upload the code to an FPGA. And now I might go to the same FPGA, or most probably I will go to a different one. So right now it's also University of Washington, but I know that this is a different one, and we were in the structure 3 instance something. So right now I'm going to a different FPGA. So basically the other FPGA right now is available. Somebody else might be using it. Maybe like one of you is using it. But basically the way it works is that it's distributed between different locations. And in this case, like I'm going to the University of Washington, but if all the FPGAs at the University of Washington are being used, we will go to different universities that provide this equipment through the LabsLand network. I'm not going to go too much in detail here, but I mean, like I wanted to do some further examples, but I don't want to go into much detail. But actually, there are many other things that you can do in this laboratory that we are not going to cover today, including the VGA part, so that I can show some, like I can use the VGA of the FPGA and will capture it, and I will see it in my computer. We also have like audio, but audio is particularly difficult to test in Zoom, like because like I mean, in this case, what I do is I can configure it, I can upload some MP3 file, and I will be able to play it to the FPGA, and then I will be able to listen what's happening from the FPGA to the FPGA. And we also have some virtual controllers, but those are like outside the scope of these workshops, so I'm not going to go into detail. Here, the breadboard one, what we support here is that we tell the student what are the inputs, like the selected inputs that you can use, and some outputs that you can use. And then in that case, I can connect like, so for example, if the number 3 is the input, number 6, so I can connect this switch to the number 6, and then I can connect the output like these two. I can connect them to, for example, 31 and 32. I can connect them here and here. So I could be connecting these wires here to the how do you call, to the breadboard. And if I do this, I will be able later to see this same user interface, and I will be able to click on the switches and see how it reacts whenever you send that one through the GPIO 6 in this case, and well, GPIO 5 actually, the pin 6, and what happens in the GPIO 26. So if my code was sending something from one side to the other, I will be able to see it in the LEDs, and I will see if these LEDs turn on or off. But once again, like if you are interested in something like this, like let me know in the chat, and I can do demos of the FPGA, I mean of the VGA or the audio, or if we have enough time, we can go to that version. But for now, we are going to focus first on the standard version, which is just the camera, switches, and buttons. And in this case, I'm going to go back to the document that I shared with you. In this document, first of all, like has, like I don't know, I'm checking just in case there is any comment or so. Before we continue, because like the next part is going to be more like the hands-on lab session, like here, I will be talking about the, like we will do some example like with the Vhdl or Verilog or System Verilog, and we will be able to use it. So before we do this part, has everyone been able to go to register first of all in the platform, like to create an account in the platform using the link that I provided? And then have you been able to go to this Vhdl or Verilog or System Verilog code? I see Hans saying yes. I'm not sure. Like so, or well, I will ask the opposite. Like, has anybody have any problem registering, like or like with any of the steps? Because I know that they went fast through them because I was just wanted to show how it works. But now for the next part, it's very important that we all can access the FPGAs and the code editors and so on. So if I need to repeat the steps just in case, if I go back to this link that you can see in Zoom, like the first one or the second one, or the one in the document. If I go to the first link that I see somewhere here, this one here, if I go here and I copy this link, I go to this space. In my case, I'm already logged in, but if it's the first time you use it, you will have the option to create an account or log in as a student. Login as a student makes only sense if you already created an account, that some of you already registered in a Google form, and like maybe some of you already created an account before the workshop. In that case, it makes sense that you click on login as a student. Otherwise, if this is the first time you're doing it, please create an account, and then you have to put a username and a password. Optionally, you can provide an email. We will not store this email for privacy reasons, but we will store kind of a hash, a salted hash of the email, so that we can guarantee that if you forget your password, if you at least remember the username, your email, like we can recover it. In my case, given that I created an account already, I'm gonna go here and say, well, now I have to remember if it was this one, I think. Yeah, it was that. So with that, you will be able to see the FPT21 tutorial FPGA. As I said before, like there is another link in the document that tells you how to use other labs. Inside these other labs, like there are many other labs, and like we will be able to. I'd like to do a couple of more demos later on, like today. But in any case, you can use it also like later on, like the other laboratories. In particular, electronics can be interesting for the same audience. Here we have the D1 system on chip, but also the D2115 and the FPGA laboratory. In any of them, like I'm going to use the D1 system on chip, you have Verilog, Vhdl, and the system Verilog. In any of them, you can click on the access button and you will be able to access the code editor. And then you will be able to synthesize your own code and so on. I'm going to explain very quickly that what is this FPGA laboratory, because obviously all of them are FPGA laboratories, but what we call the FPGA laboratory is a particular laboratory that it uses both D1 system on chip and D2115. So basically, you go to a code editor, you can write your own code, and as long as it's compatible with the subset of these FPGAs, you will go sometimes to one FPGA, sometimes to the other type of FPGA. However, for this workshop, I'm going to only use the D1 system on chip, and I'm going to use Vhdl because that's the one I'm more familiar with, but feel free to use Verilog or system Verilog. So this is the more step-by-step version. And then here in this code editor, what you have is different parts. The first part is the files that you can have. In this case, this is a very simple code that only has one file called LEDs mirror, and it has this is the code it has. But I could add more files, like either from my computer, or I can add a new file called the converter, 7-digit converter. Like I could write here other code, and then I can go from one code to the other. At any time, I can delete these files. It's very important that if I have more than one file, I properly select what is the top level entity, because otherwise, if it's the first file and then you're using another file, then it will be a problem. But in this case, I'm using this one. And then you can delete, of course, any file at any point, and you can copy the code and so on. Here you will see also the documentation about the I/O signal names, like what signal names we support. You will be able to see that we have the switches, the keys, which are the push-up buttons. There is the clock, the LEDs, the 7-segment displays, and and how they are mapped later to GPIO. If you want to go into much more detail, you can go to the QSF file. And then here you will see that actually internally we are mapping the key, for example, we are rewriting it to be the AC18, which is actually the GPIO 0. So you can see like what is internally using, but here you can use many more things because this is the standard, like with a few modifications. But you will see that you can use VGA, you can use like a GPIO directly, you can use many different options, like the like memory and so on. Also, like in these examples, we are using this code editor. However, this code editor is optional, meaning that if you prefer your student to be using Quartus, we do support that the student writes a code in their computer, they synthesize the code, they generate a SOF file, and then they upload the SOF file directly to LabsLand. That way they can access the particular FPGA directly, and they don't have to go through all this interface. And that's actually very useful in advanced levels, like a typically master like level where students are using the professional tools already. This environment is only interesting for like first steps for the student to understand like the concepts of Vhdl and so on, without having to set up the full Quartus and download like several gigabytes and so on. However, this is like a kind of like a toy for learning these kind of languages. So it's only like for the first courses of that. Otherwise, like we will encourage people to use the Quartus directly and program the code in their computer and upload it to the cloud that way. Here there are more links, and there is also examples. Depending on the language that you are using, if you are using Verilog or System Verilog, you will see different examples, or VHDL is different examples. So you will see like more complex examples where you have time to digits and second clocks, and you have like different files that you can copy and paste in this environment and synthesize it. So now, and then once again, like once you have written some code, you can synthesize this code, and then you can upload it to the FPGA. In my case, given that it was cached, then I have it takes zero time. But maybe in your case, if you're running it now, you will see that if I change here something, like I don't know, if I put here like a 10 and I synthesize. And if I haven't done that same example somewhere else. So yeah, I see that right now I will see in real time how the code is being synthesized somewhere else, like in any other university. So like we have several computers that are synthesizing continuously, like whatever code the student sends. So this is what actually students typically see. What they see is all the synthesis process, and then it takes a couple of minutes, and then they will be able to use FPGA. In this case, given that it's like such a simple code, it might take shorter, but it all depends on the particular machine that I'm using. Okay, so I'm going to wait a little bit until it finishes this code, and then we're going to go back to the Word document that I was presenting. But once again, if you have had any problem to reach this point of like being able to synthesize the code and so on, please let me know in the chat, either in Zoom. I don't know if you can write there, or otherwise in the tool in the conference tool. So here it will take some few more seconds, and then at some point, once I finish this, I will be able to change that. Yeah, this is the last step. And now this time it was 1 minute and 30 seconds. And now I can upload it to the FPGA. And in this case, I will go to another FPGA, and I will be able to do, I think, like when I click on this button, it's not a 0, it's something else, like it's like a reverse 6, but the reason is because I changed one of the 7-segment in the 7-segment display. I changed one of the LEDs, I turn it from 1 to 0, and the other one, the one in the middle, from 0 to 1. So everything else will work in the same way, but given that they only change that particular code, that's the only change that we see here. Everything else, the LEDs and so on, are working. Okay, so I'm going to go back to this document, and then in this document, well, I'm gonna check just in case anyone has any problem. Like I see that there is no message, so hopefully, nobody is having problems. Here you have the other links for more laboratories, for 3D printer, electronics, and so on. Here you have the slides that I was presenting, just in case you want to go forward, back and forth. And then in this page, you will see that I mean, the picture of some of the FPGAs in this case at University of Washington. But in this case, what we are going to do is, like, the focus of this workshop is to propose an activity that will get familiar with the online LabsLand platform and to go to the FPGA laboratory lab. And here, this link, you will be able to download a zip file. And this zip file has the lab one that has 2 parts. I'm going to close this. And then the first part, it has a well, the diagram and the PDF. And in this PDF, which was done by my colleague Luis, it includes it explains how to use the particular laboratory for a simple example. So I'm not going to go through all the steps, because many of these steps I've already presented them. Like, this is intended to be used without having to have someone explaining everything. But here you can see how the IDE works and the different versions of it, like the file management, like all these that I just explained, and how the laboratory in the end looks like. But then what I wanted to explain is this part here, where what are the switches, and this I explained already, what are the signal names and so on. We have 2 versions. One is the V underscore SW, but we also support just SW, as in the Intel language. The problem with the V is because we use it for multiple potential types of FPGAs and so on. And in problem statement, the idea is to do like the same code that I just implemented, but making it better, like to support, for example, instead of doing supporting that the student writes, that the user clicks on the switches, and with 4 of the switches, you can say we have to see in the 7-second display some number between like a 0 and F in hexadecimal, according to whatever we say with those bits in the input. So in the zip file, there is this initial code that I'm going to show very quick here. Here there is this code where there is like the binary to serpent direct. It has the 4 switches only. It has the 7-second display, like only one of them, but we have multiple, of course. So you can just like add more if you want. And then what we do here is with this, we say, okay, with these particular 4 bits, if we have show this if the 4 bits are 0, and show this if the 4 bits are F, and otherwise enable the mid segment just to show that it's something working. We could always put a 1 here as well. And what we are supposed to do in this in this lesson is to start copying here these lines, kind of, and then start saying like, okay, how will I paint a 1? And then we will go to the documentation and we will see somewhere here what is 0, 1, 2, 3, 4, 5, 6. And therefore, if I want to paint a 1, what I have to do is taking the number 1 and the number 2 to 0 and the other ones on. So I will have to do something like I think it's something like this, 1, 1, 0, 0, 0, 0. So basically the first zero, which is this one, it will be 0, then 1 and 2 will be 1, and then the rest, the other 4, which will be 3, 4, 5, and 6, should be 0. So if in case that the switches have 0, 0, 0, 1, that is the code that we should see. So this, I'm going to save it. I know I'm going to save as somewhere in my computer, like this code, the beans to save. And then I'm going to go to the remote laboratory, which is here. I'm going to delete this code as we did before, like with the trash button. And then I'm going to add the file, which is in my computer. I will take this file. And then the top level entity, given that there is only one file, it will obviously be that one. And then I will synthesize this code. And then once I synthesize, I will go back to the slides because this will take another minute. I will be able to see if this code, at least with the one, is doing what to do. So what I was going to encourage you to do is to actually like do this yourself, like because now that you can do it. Let me go back to the slides. And yeah, okay, so I think that I'm doing the example wrong, but basically like with this you can follow the guide and you can actually build the particular code. And the good thing is that yeah, you can test the code in the real FPGA. I'm not going to go through the conclusions because I wanted to show that while we are working on this, I'm going to, oh, okay, this is uploaded already. So I say that with 0, it's a 0, with F is like this. And what I added was that in the case of 1, it's going to be like this. If I upload to the FPGA, and in this case, I'm using the switches. So it says 0. If I put 1, okay, so I did it wrong. Like this E is not an E. It's like that all the ones are zeros and all the zeros are ones. So, but if I select, I think F was already done and F is correct. So the thing is like we should be doing all these examples with the other code. In this case, I know now that I had to do 1 and then 0, 0, and then how is it? 1, 1, 1, 1. And then I will synthesize this code. It will take some time again. Oh, okay. So at some point, or maybe some of you have already synthesized it, but it's already compiled. And then if I go to the FPGA, in this case, the number 1 should work. So if I go here and I select 1, then I will see a proper 1. So then, like, if we want to do the number 2 and number 3, like, so we just have to do the same in the same switches. So this is just like the tiniest example to do this. There is we have added another part 2 of this laboratory of these labs. In this case, the goal is more complex, like it's more for creating a arithmetic logic unit that lets us to choose an operation and to insert the 2 values and conduct the choice operations among them. So I'm going to skip some of the parts because this is what we were covering before, but in this case it's more complex. You have like an opcode which has 2 bits and the left operand which are 4 bits and the right operand which are another 4 bits. All of them we are using these switches and the 9 and 8 switch are the ones on the left, and then 4 more bits and 4 more bits. And if we continue, we will use the LEDs to show this and also the different hexa 7/7 displays. And then in this parallel statement, as we showed before, I mean, like this is more complex. I'm not going to go into all the detail of all of this. Let me go to the initial code that is here. for the last steps. So here you will see that we are using another component, like so we are using like we have this lab, but then we have the bin2sex, which is somewhere else. Probably it's here, bin2sex. So we have here a component that where we should be filling all the data and saying like, okay, we're going to do this the same as before. And this lab one has, we have to do, we left here some operands, like this will not synthesize because you have to change things here of what will be the right operator, the left operator, the opcode, and so on. This is a more complex example. This is more intended for being used in the class with the students. We're not going to cover this in 15 minutes. But just to give you ideas of how you can use actually this laboratory. We also have other tools like such as, I'm going to skip this part but in this case you can see that it's the lessons are more completed about all this. But I'm going to go to the show another example of another tool that we are using now with this, where you can say this is my test. This is yet another tool where you can develop at the University of Deusto in Spain, where you can have multiple inputs like input 1 and input 2 and so on, and then the output 1 and output 2, and you can put many different inputs and outputs, and then you can, what you have is a truth table where you can say this is like I'm going to put a 1 here, a 0 here, X here, and so on. And I'm going to complete the rest with ones. And then I can see what is the formulas for this. I can solve this circuit. If I solve this, I will see how it works. I can it generates automatically the ANDs and the NOR and like the NOT and the OR gates, and then I can actually test it remotely. And for that, I can say with the switch of the FPGA, with the switch number 0 and with the switch number 1, and if I put the outputs as LED 0 and LED 1, with this, once I do this, I can download the Vhdl code. I'm going to call it example, and I can open it. And yeah, so this code is basically that code that we just saw. So that this is intended for explaining in the beginning how all this works and how this can be used for those kind of systems. So that code, I could actually use it here. I'm going to delete this. I'm going to create a file called base. I'm going to paste this code. And this code I will be able to synthesize. That will take again like a couple of minutes. And then I will be able to upload this code to the FPGA. But as you see, this is exactly the same as before. And the interesting part is that this part here, right here, if I go to the truth table, I will see that it behaves as expected with that. So this is just yet another tool that we are using in the LabsLand ecosystem, and we are actually like integrating this tool in this environment soon. So that you can use it directly from this interface, so that your students can do those kind of lessons. But basically, this is just another example of the kind of things that you can do with these kind of remote laboratories without having to have all the equipment or to have to go to the laboratory. And I mean, this is something you can do in the class of theory. And so on, and the students can actually do it in their cell phones, in their tablets, like in the iPad or whatever, and they can use it at any time, anywhere, which is like one of the reasons for it to be so exciting for using in the classroom. So I'm going to wait. It should be almost ready, and then I will go back to the slides. Okay, this is the last step, so it will be a couple of seconds. Okay, so I'm going to upload the code to one FPGA. I will go to another FPGA, and then now I will go to the FPGA, and then it's The output is a 1. Where was the output? But these inputs that were somewhere else, I think it's because it's this. So if I change this, it's going to be changing, and it will be changing the other parts. This, it says 8 because given that we didn't connect anything, it's all zeros, and therefore like it's all on. So that's how we will have to change it if we wanted to do it in different way. But these two buttons are using this truth table. So if I turn on the both switches, we saw 1 1. If I don't do anything, if I put 0 0, I was seeing 0 1. If I want to see 0 1, it will be 1 and something that we don't know. It doesn't matter what it is. So if I go to this, to this one is 1 and this one is 0, and that's compliant with this definition that we built. So I'm going to stop this, and I'm going to, because it's only 10 minutes left. I'm going to check it just in case you have any question. I don't see any question here or there. So in this case, like going back to the slides, like there are other links here for more labs. You also have the slides of the workshop, and then Q&A. Like if you have any question. And I also going to go to the other group, to the other labs. And here there are the robot that I showed before. There are other laboratories like 3D printer that I showed before. I'm going to use the electronics one, which is not related to FPGAs, but it's yet another laboratory that is also very popular. And in this case, what I do is I can select, for example, resistors, or I can connect cables like from the oscilloscope. I can connect something to a function generator, and here I have a full function generator that I can control. I can change the type of wave, and I can go to the oscilloscope and then take a measurement. And this measurement is taken right now from a real equipment. Like this is not a simulation. It looks like a simulation because it's all painted in my screen, but it's actually a real equipment that I showed before somewhere here. It was right here. This laboratory is actually, it has a set, it's called Vizier from the Black Institute of Technology in Sweden, but we have deployed it in different locations, and it has several boards that they has a lot of relays. It has like several components. So whenever I'm connecting something to something, it's actually connecting these relays to build actually physically the circuit and connect it to this equipment that has the multimeter, oscilloscope, and other components. So this is the simplest the simplest thing. But if I go to the next page, you will have like an example, which is I think a rectifier, and I can save it in my computer. And if I go here and I load it, here it is. Like in this case, I have a diode and a resistor, and I can go to the oscilloscope and take a measurement, and I can compare, and I can play later with the diode. I could change it and move it wherever, and I can play with the function generator and so on, and I can do all the tests for all this. If I also connect like resistors and so on, I can connect resistors here and there. I can connect this to the multimeter. Let me see here and here. And then if I go to the multimeter and I take the measurement, I will see like the 10 ohms plus 1, I think. Yeah, 10 plus 1. I see that the result is 11 ohms. I have the DC power that I can control, so like the 6 volt, the 25 volt, the minus 25, and so on. So with all this, I can do the tests, and this one is hosted at the University of Deusto, but as I said before, we have in different locations, and this one, like you have like 2 hours, but actually you are using the equipment only a fraction of a second. Every time I click on this button, only for a fraction of a second, I'm taking the measurement. So if we have like many students at the same time, even using the same equipment at the same university, they just like have a micro queue, like that it takes like less than a second for each request. So in the worst case scenario, the student will have to wait a couple of seconds to get their result back. And that's how this laboratory works. So I encourage you to take a look at the other labs. If you don't see it, it's because you haven't clicked on this link, the one of more labs, or if you go to the slides, it's also somewhere here, FPT, here, more labs. So if you go to the click of more labs, you will be able to join that group, and therefore you will be able to use the other laboratories. So with this, we covered everything that we wanted to cover in this workshop. I don't know if you have any question, like you can ask in the discussion forum. Like I think, oh, okay. So you actually, sorry, I thought that it was a discussion forum. I wasn't seeing this. So Julian, okay, 2 seconds ago, asked, do you have protections against students trying to destroy the equipment by shorting a circuit or overloading the FPGA? We do have certain protections for the laboratories. In the case of the what's the name? In the case of the circuits, the electronics laboratory that I showed, that where you can put, you could build shortcuts and so on. However, we have a whitelist of what exactly can be done, like another list of what can be connected, precisely to avoid problems of like students connecting what they shouldn't and burning the lab or something like that. So in that case, we do have protections. In other laboratories, like the FPGAs and so on, we do have other types of protections, like with resistors and so on, to avoid problems if a student is sending something that they shouldn't, but up to a certain level. And that's some of the challenges with the Jose, with the in the remote laboratories, you always have the thing that is always real equipment. What we have is, for example, in the case of the robot, we do have systems to automatically detect if there is any problem. So we have systems that are like in the case of the robot that I showed in the beginning, we have every few hours it's being some code is being sent to check with the computer vision to check if the robot is following the line or not. And if the robot is not following the line in the way they are supposed to, then automatically we will assume that there is some kind of problem, maybe with the motor or maybe with something, and that robot will not be in the pool, so the students will not see that robot anymore. So we are controlling all the robots very often to make sure that they work. We do similar tests with the other laboratories with FPGAs regarding like the cameras and like everything else. We do run tests to check that everything is working as it's supposed to. And let me see. And yeah, so if there's no further question, I think we can finish here. You have this space for testing the tool and so on, and to allow it. We will open it for over a week, the particular space, so you can use it and play with it and so on. If you would like to either to join LabsLand either as a provider, meaning having your own equipment, or as a consumer, meaning that you can access the laboratories from third parties, or a prosumer, which is the most it's very common that universities that are providers are also consumers of other laboratories. Just let us know. We put the email of the of FPGAs at labsland.com. Or my email is in the slides as well, and I think I put it in several places, in here it's FPGA. Well, I didn't do a very good job there of putting it very big. But yeah, with this you can contact our whole team. So feel free to contact us for any further information or any of the topics that we didn't cover in this workshop, including the VGA part or the audio or anything like that. So thank you very much for staying for being in this session, and once again thank you Intel for all the support for this.
Thank you very much, Pablo. Much appreciated.
So we're going to have a short 10-minute break here today, and yeah, then at 12:10 there's next talk. RV FPGA SoC, how to go from a RISC-V core to a RISC-V SoC. See you then. Bye. And thanks, Pablo, again. Bye.